In the vast family of Jupiter's moons, one stands out as a shimmering beacon of potential alien life: Europa. Welcome back to Infinity Beyond, where today we take a closer look at this mysterious, icy world, one that might just be hiding an ocean beneath its frozen surface. Europa is one of the 4 Galilean moons, and arguably the most scientifically intriguing of them all. What makes it so exciting? Unlike volcanic Io or massive Ganymede, Europa's surface is composed almost entirely of water ice, and beneath that lies strong evidence of a global subsurface ocean. The first close-up image of Europa was captured by the Pioneer 10 probe in 1973. It showed a pale, fractured surface unlike anything seen before, an icy crust etched with reddish lines that look like veins stretching across the moon. Later missions, including Voyager 1, Voyager 2, and especially Galileo, gave us clearer views and more data. Europa's surface is relatively smooth, with very few impact craters, suggesting it is geologically young and constantly reshaped. This renewal is likely caused by upwelling from below, the icy equivalent of tectonic movement. Some of these surface cracks are filled with darker material, possibly from the liquid layer beneath or impurities in the ice. But the real revelation came from magnetic measurements. Galileo's data showed that Europa has a magnetic field that behaves as if it were generated by a conductive liquid layer, likely a salty ocean beneath the ice, perhaps as much as 100 kilometers deep. That's more water than all of Earth's oceans combined. Moreover, astronomers have observed plumes of water vapor erupting from Europa's surface, especially near its south pole. These plumes suggest that the ocean beneath is not just theoretical, it's actively communicating with the surface. These geysers could potentially be sampled by spacecraft without needing to drill through kilometers of ice. What does this mean for life? Well, here on Earth, life thrives in the dark, cold environments of hydrothermal vents on the ocean floor. These ecosystems require no sunlight, just water, heat, and chemical energy. If Europa has similar vent systems on its ocean floor, heated by tidal forces and possibly a rocky seafloor, it could provide a habitable environment for microbial or even more complex life forms. Scientists have found signs of salts, carbon compounds, and possibly even organic molecules on Europa's surface, all elements linked to life. The reddish lines crisscrossing the moon may contain these organic materials, delivered from below or created by radiation interacting with the ice. Color-coded images also show different particles being ionized around Europa: green for sodium, red for oxygen, and blue for sulfur. These colorful emissions point to ongoing interaction between Europa's surface and Jupiter's intense radiation environment, which bombards the moon constantly. Despite this harsh radiation, the thick ice shell could serve as protection for any life forms in the ocean beneath. And just like Earth's polar oceans are teeming with life under the ice, Europa may be harboring similar mysteries. To explore these possibilities, NASA is preparing the Europa Clipper mission, set to launch in the coming years. This spacecraft will perform dozens of flybys of the moon, using radar, spectrometers, and cameras to scan its surface and measure subsurface features. It will even attempt to fly through the plumes if they're active, sampling their chemical makeup directly. If successful, Europa Clipper could help answer one of humanity's oldest questions: are we alone? Because if life can emerge on Europa, an icy, sunless moon hundreds of millions of kilometers from Earth, then life could be far more common in the universe than we once believed. As we leave this icy moon, we recognize that Jupiter's system is not just a collection of satellites. It's a miniature solar system full of active, dynamic, and potentially habitable worlds. In our next episode here on Infinity Beyond, we set our sights on Ganymede, the largest moon in the entire solar system, a world with its own magnetic field, layered structure, and yet another possible ocean. While we've explored Jupiter through telescopes and flybys for decades, nothing has brought us closer to the planet's true nature than NASA's Juno mission. Welcome to Infinity Beyond, where today we uncover the astonishing discoveries made by Juno, unveiling what lies beneath Jupiter's iconic stripes and storms. Launched in 2011 and arriving at Jupiter in July 2016, Juno's mission was clear: go deeper, get closer, and reveal what previous missions couldn't. It entered a highly elliptical polar orbit, allowing it to swoop close to the cloud tops and then fly out far beyond the radiation belts, making it the first mission designed to both survive and study Jupiter's extreme environment up close. One of the most groundbreaking findings involves Jupiter's atmospheric structure. Prior to Juno, we believed the bands and storms were confined to a shallow atmospheric layer. But Juno's gravity measurements revealed that these bands extend deep into the planet, up to 3,000 kilometers below the cloud tops. That's more than we expected, and it means that Jupiter's weather isn't just skin deep. It's a planetary phenomenon that permeates much of its outer envelope. Juno also studied the Great Red Spot, that massive storm we've all seen in countless images. Using its microwave radiometer, MMWR, Juno found that the storm plunges deep into the atmosphere, deeper than any Earth hurricane, and has a complex thermal structure that gives it surprising longevity. Juno's magnetometers have mapped Jupiter's magnetic field in unprecedented detail. What they found was surprising. The field is not symmetrical. The strongest part is offset from the planet's center, indicating a lopsided dynamo effect deep inside. This discovery is helping refine our models of how planetary magnetic fields are generated, not only for Jupiter, but for exoplanets and even Earth. Even more surprising were findings beneath the clouds. Juno confirmed that Jupiter does not have a solid surface in the traditional sense. Instead, as we move inward, gases compress into liquid metallic hydrogen, a state of matter that behaves like both a metal and a fluid. This region likely supports the currents that generate the magnetic field. But what about the core? Juno found evidence suggesting that Jupiter's core is diluted or diffuse, perhaps a massive mix of rock, ice, and hydrogen, spread over a larger region than previously believed. This finding may be the result of an early giant collision during Jupiter's formation, blending core material with lighter elements and changing its internal composition permanently. Juno has also delivered stunning insights into Jupiter's auroras. Unlike Earth, where auroras are mostly triggered by solar wind, Jupiter's are powered by its rapid rotation and interaction with its moons. Juno's ultraviolet and infrared instruments showed intense, persistent auroras dancing at the poles, many powered by Io's volcanic emissions and other internal mechanisms. Beyond Jupiter itself, Juno has flown close to Ganymede and Europa, capturing high-resolution images and valuable magnetic field data. These flybys have provided more context for understanding how Jupiter's system works as an interconnected whole. Moons, fields, radiation, and all. And Juno is still going. Its mission has been extended into the late 2020s, with plans to explore Io in greater detail. These extended orbits will allow the spacecraft to fly even closer to some of the most active and mysterious moons in the solar system. Perhaps most importantly, Juno is showing us how gas giants function as complex, layered systems. Its findings are helping scientists rethink planetary formation models and offering clues about how giant exoplanets around distant stars might behave. With each orbit, Juno sends back more than data. It sends wonder. It reminds us that even the largest and most studied planets can hold surprises, waiting patiently in their swirling clouds. Next on Infinity Beyond, we will explore how the formation of Jupiter shaped the rest of the solar system. What would our cosmic neighborhood look like if Jupiter had never formed. Jupiter holds a vital role in protecting our solar system. And today, it's time to unravel its deepest mysteries. Welcome to Infinity Beyond, where the cosmos becomes your classroom. In this episode, we explore everything you've ever wanted to know about Jupiter, the fifth and perhaps the most influential planet from the Sun. Located on the outer edge of the asteroid belt, Jupiter resides between Mars and Saturn. It orbits the Sun at an average distance of 778 million kilometers, or about 5.2 astronomical units. Each of its years takes 12 Earth years to complete. With a minor axial tilt, Jupiter experiences minimal seasonal variation compared to Earth. What sets Jupiter apart isn't just its immense size, it's the gravitational power it wields. This gas giant contains more than twice the mass of all other planets in the solar system combined. It has such immense gravity that it can actually influence the Sun's motion slightly. Jupiter's gravity acts like a cosmic vacuum cleaner, pulling in comets and asteroids that might otherwise pose threats to the inner planets, including Earth. Its powerful magnetic field is unmatched, stretching millions of kilometers into space, forming a magnetosphere so vast it would appear several times wider than the Sun itself. This magnetosphere traps deadly radiation belts that any spacecraft must navigate carefully. Despite its violent storms and deadly radiation, Jupiter has a captivating beauty. The iconic bands of clouds, swirling in shades of cream, red, brown, and white, are driven by fierce jet streams blowing at hundreds of kilometers per hour. And who could forget the Great Red Spot, a persistent high-pressure storm system that has raged for over 300 years. But there's more beneath the surface, or rather, beneath the clouds. Jupiter doesn't have a solid surface as Earth does. Instead, it transitions from gas to liquid metallic hydrogen under immense pressure, possibly surrounding a core that's still a subject of debate among scientists. We've only begun to scratch the surface of what this gas giant has to offer. With missions like Juno, which continues to orbit Jupiter today, and future missions like the European Space Agency's JUICE and NASA's Europa Clipper, humanity is poised to uncover even deeper secrets hidden within this mighty world. So why is Jupiter so important to us? Beyond scientific curiosity, it plays a protective role. Its gravitational pull deflects and absorbs many comets and asteroids that could otherwise reach Earth. Some even theorize that without Jupiter, complex life on our planet might never have had a chance to evolve. As we peer deeper into this swirling behemoth, we realize that Jupiter isn't just another planet. It's a gatekeeper, a guardian, and a key to understanding how our solar system was built. Stay tuned with Infinity Beyond as we journey further into Jupiter's storms, moons, and mysteries in our next chapter. The Great Red Spot of Jupiter is more than just a colorful feature. It's a centuries-old storm system that has fascinated scientists since its discovery. Despite being studied for hundreds of years, many of its characteristics remain elusive. Its true origin is unknown, and even its coloration remains somewhat of a mystery. The color of the Great Red Spot can vary significantly, ranging from a deep brick red to a pale, almost white hue. One prevailing theory suggests that the red coloration results from chemical compounds in Jupiter's atmosphere being broken down by ultraviolet light from the Sun. This process is similar to what occurs across other areas of the planet, but the spot is unique in its structure and altitude. Interestingly, the Great Red Spot exists much higher in the atmosphere than the surrounding cloud layers. This elevation allows it to interact with sunlight more directly and intensively, which could explain the boldness of its color compared to the muted bands around it. The more intense the interaction with UV radiation, the more pronounced the coloration appears. But the Great Red Spot is not merely a colorful blemish. It's a storm of unimaginable proportions. Spanning over 16,000 kilometers at one point, it's large enough to engulf Earth 1.5 times. Winds inside the storm can reach speeds of up to 430 km/h, and yet the storm itself moves relatively slowly, rotating counterclockwise every 6 Earth days. Despite its massive scale, the storm has been shrinking over the past few decades. While this may seem alarming, scientists believe it is part of a longer cycle of atmospheric change on Jupiter. What appears to be a decrease in size may, in fact, be a transformation, perhaps a shift in the planet's meteorological patterns, or a temporary phase in the storm's evolution. The behavior of the Great Red Spot provides valuable insight into fluid dynamics, especially on a planetary scale. Jupiter's atmosphere lacks a solid surface to interfere with wind patterns, allowing storms to persist far longer than those on Earth. The massive energy dynamics and the Coriolis effect, resulting from the planet's rapid rotation, allow for stable yet dynamic systems like the Great Red Spot to persist for centuries. In recent years, spacecraft like Juno have provided unprecedented data. Juno's suite of scientific instruments has allowed us to peer beneath the visible cloud tops and study the structure of the storm in greater detail than ever before. What's been found is astonishing. The roots of the storm may extend over 300 kilometers deep, possibly involving layers of compressed liquid and even metallic hydrogen. Even more surprisingly, the Juno mission revealed that the red spot is not just an isolated anomaly. There are multiple smaller storms that orbit around Jupiter and even merge with or affect the Great Red Spot. These interactions offer a fascinating look at atmospheric chemistry and energy transfer on a scale not possible anywhere else in the solar system. But why do we care so deeply about Jupiter's storms? Beyond their aesthetic beauty, they offer a natural laboratory to study the extreme conditions of gas giants. The behavior of these storms can help us understand atmospheric patterns on exoplanets and even the early history of gas giants in other solar systems. Moreover, by observing how such a persistent weather system evolves, scientists hope to improve models of Earth's own climate systems. Despite the vast differences in size and composition, there are universal principles that govern the behavior of fluids and gases, and Jupiter is one of the best places to test them. As we continue our journey through the mysteries of Jupiter here on Infinity Beyond, we'll explore not only the dramatic tempests like the Great Red Spot, but also the more subtle processes shaping the entire planet. Stay with us as we dive next into the powerful magnetosphere of Jupiter, an invisible shield so massive it makes Earth's magnetic field look like a drop in the ocean. In the grand theater of Jupiter's moons, Callisto often plays a quieter role. Unlike the volcanic fury of Io, the magnetic complexity of Ganymede, or the mysterious ocean of Europa, Callisto wears its age in every crater and ridge. But don't be fooled. Beneath this ancient surface may lie one of the solar system's most intriguing secrets. Welcome back to Infinity Beyond, where today we explore the oldest, most heavily cratered moon of Jupiter. Callisto's surface is a mosaic of impacts, unchanged for billions of years. It's one of the most cratered bodies in the solar system, suggesting that geological processes here have slowed to a crawl or ceased entirely at the surface. And yet, beneath this static exterior, there may be hidden activity. Scientists estimate that Callisto, like its sibling moons, may harbor a subsurface ocean. Magnetic field data, gathered by the Galileo spacecraft, hints at an electrically conductive layer beneath the icy crust. If true, this ocean may lie more than 100 kilometers below the surface, trapped beneath a thick shell of ancient ice. Unlike Ganymede or Europa, Callisto doesn't appear to have active tectonics, resurfacing, or volcanic activity. That might seem boring, but it also means its ocean, if present, could be chemically different and perhaps more stable over immense spans of time. In planetary science, stability can be just as important as energy when it comes to supporting life. Callisto also has a thin oxygen atmosphere. It's almost imperceptible, measured between 0.2 to 1.2 micropascals. That's roughly 100 billion to 500 billion times thinner than Earth's atmosphere at sea level. Far too thin to breathe and far too unstable to support surface life. Still, Earth has shown us that life can flourish in the most extreme environments, from deep-sea hydrothermal vents to subglacial lakes in Antarctica. So the possibility, however remote, that microbial life might survive beneath Callisto's crust is a question worth asking. One advantage Callisto has is its relative radiation safety. While Europa and Ganymede are bombarded by Jupiter's intense magnetosphere, Callisto orbits further out, beyond the most dangerous radiation belts. This could make it a better candidate for long-term robotic or even human exploration. Some scientists have proposed that Callisto could serve as a future base for missions deeper into the outer solar system. Its stability, low radiation, and potential access to water ice make it a compelling logistical waypoint. Its massive surface craters, like Valhalla and Asgard, stretch thousands of kilometers and reveal a complex internal structure, layered ice, possible liquid zones, and a rocky core. Radar instruments aboard future missions, like JUICE, will help confirm whether an ocean really exists below and what conditions might be like in that dark buried sea. Despite its ancient surface, Callisto may hold clues to the early history of the solar system. It likely hasn't undergone significant change in billions of years, meaning it acts as a time capsule. Studying its ice, rock, and trapped elements could give us insight into what the primordial solar nebula was like when Jupiter and its moons first formed. Callisto's silence is deceiving. It may not erupt or glow or roar with auroras, but in its quiet, cratered stillness, it guards mysteries as deep and powerful as those of its more famous siblings. As we continue our journey through Jupiter's vast moon system here on Infinity Beyond, we recognize that even the quietest worlds have stories to tell, some stretching back to the dawn of time. Next up, we'll zoom back out and look at Jupiter's magnetosphere itself, an invisible force field so large it would engulf the Sun. What is it? How does it work? And how does it connect the entire Jovian system into one giant magnetic machine? Among all the moons in our solar system, one stands as the undisputed giant Ganymede. Bigger than even the planet Mercury, Ganymede is more than just large, it's magnetic. Welcome to Infinity Beyond, where today we unlock the mysteries of the solar system's largest moon and the only one known to have its own magnetic field. For decades, Ganymede was a quiet giant, its features veiled by distance and assumption. But in 1979, NASA's Voyager spacecraft delivered our first close-up glimpses. Then, in the late 1990s, the Galileo probe changed everything. Between these missions, scientists detected a surprising and drastic shift in Ganymede's magnetic field. That's important, because such a shift isn't possible unless something is generating the field from within. A fluid, conductive layer acting like a planetary dynamo. This discovery was the first solid evidence that Ganymede has a subsurface ocean, likely composed of salt water, buried beneath a thick crust of ice. What makes this even more intriguing is how Ganymede rotates. Its icy crust doesn't behave like a solid fixed shell. Instead, it rotates with a wobble, about 80 degrees, which suggests the outer ice is decoupled from the interior rock mantle. This mechanical independence implies the presence of a liquid layer in between. Imagine this. Ganymede has a metallic core like Earth, a rocky mantle, a global ocean possibly hundreds of kilometers deep, and then an icy crust. It's essentially a planet-like body trapped in moon form. The magnetic field of Ganymede doesn't just exist, it interacts with Jupiter's massive magnetosphere. This creates auroras at both of Ganymede's poles, visible in ultraviolet light. Hubble Space Telescope observations have even caught these auroral ovals shifting, supporting the theory of an ocean that influences the magnetic behavior. The presence of a magnetic field is significant. It means Ganymede has an active, differentiated internal structure, something once thought exclusive to planets, and it might help protect the Moon's surface, or subsurface, from Jupiter's intense radiation. Even more fascinating, Ganymede might have multiple layers of ocean, sandwiched between high-pressure forms of ice. Under extreme pressure, water ice changes structure, forming exotic versions like Ice 6 or Ice 7. Some models suggest Ganymede's interior could contain stacked oceans, separated by dense ice layers. Ganymede's surface, too, tells a complex story. It's split between dark, older regions covered with impact craters, and lighter, younger areas crisscrossed with ridges and grooves, possibly caused by tectonic stretching of the ice shell. These terrains hint at a dynamic past, and perhaps even ongoing slow shifts today. Ganymede also has a tenuous atmosphere, composed mostly of oxygen, but it's far too thin to support life on the surface. If life exists here, it would have to be in the depths, beneath the ice, where the liquid water meets rock and heat may be generated from tidal flexing and core dynamics. The upcoming JUICE mission, Jupiter Icy Moons Explorer, from the European Space Agency will focus heavily on Ganymede. Slated for arrival in the 2030s, JUICE will become the first spacecraft ever to orbit a moon other than our own. It will carry radar instruments to probe beneath Ganymede's crust, magnetometers to map its field, and spectrometers to analyze surface composition. By studying Ganymede, scientists hope to better understand how ocean worlds form, how magnetic fields evolve, and whether this colossal moon could one day support life, or teach us how life may arise elsewhere. As our journey through the Jovian system continues here on Infinity Beyond, we realize Ganymede is not just a moon, it's a window into the complexity and potential of icy worlds. Next, we'll visit Callisto, the ancient and cratered moon of Jupiter. With its heavily scarred surface and possible underground ocean, it may hold secrets as old as the solar system itself. As we conclude our journey across the swirling bands, volcanic moons, magnetic storms, and hidden oceans of Jupiter, one truth rises above them all. Jupiter is far more than just a planet. Welcome to the final episode of our series here on Infinity Beyond, where today we reflect on what Jupiter truly represents for science, for Earth, and for our place in the cosmos. From our earliest telescopic glimpses to Juno's stunning flybys, Jupiter has challenged our assumptions again and again. It is not just a gas ball spinning in space. It is a miniature solar system, complete with dynamic weather, active moons, and mysteries we're only beginning to understand. In September 2022, Juno flew just 351 kilometers above the icy crust of Europa. The image it sent back of ridges, cracks, and shadows along the terminator line between night and day looked more like a world than a moon. That's the wonder of Jupiter's system. Its satellites are not side characters. They are destinations. Jupiter's influence stretches far beyond gravity. It taught us about planetary formation, the power of magnetism, the dangers of cosmic collisions, and even the conditions for life itself. Its storms help us model atmospheres on exoplanets. Its auroras show us how moons can interact electrically with their parent planet. And its sheer size and mass remind us of how delicate the balance of our solar system really is. It is also a planet of firsts, the first planetary auroras seen beyond Earth, the first observed impact, Shoemaker-Levy 9 on another planet, the first extraterrestrial volcanoes, on Io, the first solid evidence of subsurface oceans, Europa and Ganymede. Jupiter is also a planet of protection, a cosmic bouncer that deflects threats and gives Earth a fighting chance. And possibly, without it, we might never have evolved to ask these questions in the first place. But perhaps the greatest gift Jupiter offers is perspective. Looking into that massive stormy eye, the Great Red Spot, or tracing the orbit of its 90-plus moons, we're reminded that Earth is not the center. We are part of a much larger, older, more complex cosmic story. And as we discover thousands of exoplanets, many larger and stranger than Jupiter, we return to our own system with new eyes. Because it's not about finding something better than Jupiter. It's about understanding what Jupiter is and what it tells us about the universe we live in. So why does Jupiter matter? Because it anchors our system. Because it fuels our curiosity. Because it connects us to the stars, to the past, and to the infinite. Here at Infinity Beyond, we hope this journey has inspired you to look up a little more often and wonder, just as Galileo did over 400 years ago, what other worlds lie waiting. And with that, our voyage through Jupiter concludes for now. Until next time, keep exploring, stay curious, and remember, the cosmos is vast, but understanding begins with asking. It's hard to imagine our solar system without Jupiter. After all, it's the largest planet, the guardian of the inner worlds, and a gravitational force unlike any other. But what if one day Jupiter simply vanished? What would happen to Earth, to Mars, to the asteroid belt? Welcome to Infinity Beyond, where today we dive into a chilling cosmic thought experiment. First, let's be clear. If Jupiter disappeared instantly, the rest of the solar system wouldn't spiral into chaos overnight. The planets don't orbit Jupiter. They orbit the Sun. So, Earth's orbit would remain largely unchanged at first, but the real consequences would unfold over time, in subtle yet powerful ways. One of Jupiter's most important roles is that of a cosmic vacuum cleaner. Its immense gravity captures or deflects thousands of comets and asteroids every year. Without Jupiter, many of those objects would continue their path unchecked, and some would eventually cross Earth's orbit. In other words, no Jupiter means a much higher risk of catastrophic impacts on Earth and the other inner planets. Simulations show that the rate of large object collisions could double or even triple without Jupiter's protective gravity well. Over millions of years, this could increase extinction-level events, wiping out life before it even has a chance to evolve again. Jupiter also plays a critical role in stabilizing the solar system. Its mass helps regulate the orbits of other planets and smaller bodies. Without it, gravitational tugs from Saturn and even Neptune could eventually nudge planets like Mars or Earth into more eccentric orbits, disrupting climate patterns, causing glaciation, or possibly making the system unstable over billions of years. The asteroid belt, which lies between Mars and Jupiter, owes its very existence to Jupiter's gravity. If the planet were gone, those millions of rocky fragments could be disturbed, flung into new orbits, or form unstable groups, leading to more collisions and more debris entering the inner solar system. But not all changes would be bad. For instance, without Jupiter, the outer solar system would become less radiative. Moons like Europa and Ganymede would experience fewer auroras and less magnetic interference. Radiation levels near Jupiter are some of the highest in the solar system, dangerous for spacecraft and any potential future explorers. That said, the benefits wouldn't outweigh the risks. Without Jupiter, Earth's long-term stability could be compromised. Over millions of years, its orbit might shift. Its chances of encountering stray comets would rise, and the solar system as a whole would become more chaotic, less like the calm clockwork system we know, and more like a cosmic pinball machine. Jupiter has also played a huge role in shaping the evolution of life. Some scientists even suggest that Earth's water, The oceans we depend on may have been delivered by icy comets redirected by Jupiter's gravitational slingshot. No Jupiter might mean no oceans, no complex life, no humans. In terms of space exploration, losing Jupiter would mean losing one of the most scientifically valuable worlds. Its magnetosphere, moons, and internal structure offer insights into gas giants across the galaxy. Without it, we'd be missing a blueprint for understanding the many Jupiter-like exoplanets we've found around other stars. And finally, there's the psychological loss. Jupiter is a visual giant. Even small telescopes can spot its bands and moons. It's a familiar face in the night sky, a constant in our understanding of the cosmos. So, what if Jupiter disappeared? We'd lose our shield, our regulator, our scientific laboratory, and one of our most iconic planetary companions. Earth might survive, but it would be far less safe, far less stable, and perhaps far less special. In our next chapter here on Infinity Beyond, we'll explore how Jupiter compares to exoplanets found beyond our solar system. Is Jupiter typical, or is our giant a cosmic outlier? When we look at Jupiter today, it's easy to be awestruck by its size, storms, and moons. But Jupiter's role in the solar system goes much deeper. It helped shape the very architecture of our planetary neighborhood. Welcome back to Infinity Beyond, where today we uncover how Jupiter became the cosmic architect of our solar system. To understand Jupiter's influence, we must go back 4.6 billion years to the formation of the solar system. A giant cloud of gas and dust, known as the solar nebula, collapsed under gravity, forming our sun at the center. Surrounding it, material began to coalesce into planets, moons, and asteroids. Jupiter was the first planet to form, and it did so quickly, within just a few million years. Because it grew so massive so early, Jupiter shaped everything that followed. Its immense gravity cleared its orbital path of debris, disrupted neighboring material, and created gravitational resonances that sculpted the asteroid belt and even helped determine where other planets could form. One of Jupiter's most important roles was protecting the inner solar system. Its gravity captured or flung away countless icy and rocky bodies that might otherwise have bombarded the forming Earth, Mars, and Venus. Without Jupiter, the inner planets might have faced a much harsher environment, and Earth's delicate balance could have been impossible to maintain. At the same time, Jupiter may have also disrupted planet formation. Some theories suggest that its migration through the early solar system, possibly moving inward before settling in its current orbit, influenced the size of Mars, preventing it from growing as large as Earth. This inward and outward motion, known as the Grand Tack hypothesis, proposes that Jupiter's movement helped clear the inner solar system and shape the distribution of rocky planets. Jupiter's formation also affected the distribution of water. It may have redirected icy comets toward Earth, helping deliver the water that fills our oceans today. That means we don't just owe Jupiter our safety, we may owe it our very existence. As the largest source of gravity besides the Sun, Jupiter continues to influence the orbits of asteroids, comets, and even distant Kuiper belt objects. Many Jupiter family comets, for instance, have orbits shaped directly by the gas giant's gravity. The asteroid belt itself is partly a result of Jupiter's presence. Instead of forming into a planet, the material between Mars and Jupiter was disrupted by Jupiter's gravity, kept from coalescing into a single body. As a result, it remains a band of rocky remnants, home to some of the oldest material in the solar system. Even the Trojan asteroids, clusters of rocks that travel in Jupiter's orbit, exist because of gravitational equilibrium points created by the planet. These stable zones have become cosmic repositories, capturing debris that's remained untouched for billions of years. The implications of Jupiter's actions reach far beyond our own system. As astronomers discover gas giants around other stars, they're learning that the presence and position of such planets plays a pivotal role in shaping exoplanetary systems. Some hot Jupiters migrate inward and destroy their inner planets, while others, like ours, may help stabilize regions where rocky, potentially habitable planets can exist. Jupiter didn't just appear, it molded the solar system's layout, influenced Earth's chances for life, and continues to act as both protector and disruptor in the cosmic ballet of planets. In our next episode here on Infinity Beyond, we'll look at Jupiter's ring system, yes it has one, and what it tells us about the planet's hidden dynamics and interactions with its moons. Some moments in astronomy are so dramatic, they redefine our understanding of the universe. One such moment occurred in July 1994, when a comet named Shoemaker-Levy 9 slammed into Jupiter. Welcome to Infinity Beyond, where today we revisit one of the most spectacular cosmic events ever observed. The impact wasn't just visually stunning, it was also scientifically profound. Shoemaker-Levy 9, often abbreviated as SL9, was no ordinary comet. It was massive, so large that scientists estimated events of its scale might occur only once every 6,000 years. And unlike most celestial bodies, this one wasn't intact when it struck. SL9 had been previously captured by Jupiter's powerful gravity, which tore it apart during an earlier close encounter. What resulted was a train of over 20 separate fragments, each following a highly eccentric orbit around the planet. Eccentricity in this context measures how stretched an orbit is. 0 for a perfect circle, 1 for a hyperbolic escape. SL9's orbit had an eccentricity approaching 1, marking it as highly elongated and chaotic. These fragments entered Jupiter's atmosphere over several days, slamming into the planet at speeds exceeding 60 kilometers per second. The impacts created plumes that rose thousands of kilometers into space. Each collision released energy equivalent to millions of megatons of TNT, dwarfing even the most powerful nuclear devices on Earth. What scientists witnessed was astonishing. The explosion scars were larger than Earth itself, dark, bruised blotches in Jupiter's upper atmosphere that persisted for months. Through visible and infrared telescopes, researchers recorded how the atmospheric layers were disturbed and how shock waves spread out from the impact zones. But the real scientific gold lay in what the event revealed. First, it proved that large celestial collisions are not relics of the early solar system. They still happen today. Second, it demonstrated Jupiter's critical role as the solar system's cosmic vacuum cleaner. The planet's immense gravity captured SL9 and prevented it from possibly heading toward Earth or other inner planets. Spectral analysis of the impact plumes allowed scientists to detect molecules and elements buried deep in Jupiter's atmosphere. Ammonia, hydrogen cyanide, and sulfur compounds, normally hidden beneath layers of clouds, were blasted into the upper levels, providing rare insight into the planet's inner chemistry. Additionally, the event sharpened humanity's approach to planetary defense. It served as a reminder of how vulnerable Earth is to cosmic impacts and how vital Jupiter's shielding presence might be. Scientists began to take asteroid tracking more seriously after witnessing what such an impact could do on a planetary scale. The visual record of the SL9 collision also changed public perception of planetary science. For the first time, people around the world saw real-time evidence of space being violent, dynamic, and unpredictable. Schools, observatories, and news outlets covered the event, inspiring a new generation of astronomers. In many ways, the SL9 impact made Jupiter a more relatable planet. Not just a distant gas giant, but a dynamic, active body, engaged in ongoing cosmic drama. And this wasn't just about Jupiter. The lessons learned applied to other gas giants, exoplanets, and impact science across the cosmos. Today, we still study the aftermath of Shoemaker-Levy 9. The event shaped how missions like Juno, JUICE, and Europa Clipper are designed. Instruments are better equipped to capture dynamic atmospheric changes and identify high-energy interactions caused by such collisions. As we continue our journey into Jupiter's world here on Infinity Beyond, the legacy of SL9 reminds us that the universe is far from static. It's alive with movement, impact, and transformation. In our next chapter, we turn inward to explore Jupiter's mysterious core, its immense internal pressure, and what might lie beneath those thick, swirling clouds. Jupiter doesn't just dominate with its size or storms. It rules with an invisible force field so vast it could engulf the Sun. This is the magnetosphere of Jupiter, and today on Infinity Beyond, we'll uncover how this giant magnetic domain shapes the entire Jovian system, and why it's unlike anything else in the solar system. Jupiter's magnetosphere is the largest and most powerful of any planet, stretching as far as 7 million kilometers toward the Sun and flaring out to 650 million kilometers on the night side. That's nearly to the orbit of Saturn. Its magnetic moment is 20,000 times stronger than Earth's, generated by the motion of metallic hydrogen deep within the planet's interior. One key to understanding this immense force field lies with its moons, especially Ganymede, which has its own mini-magnetosphere embedded within Jupiter's. Scientists believe that tidal forces in Ganymede's early history stretched and heated its interior, warming the core and possibly preserving the magnetic field we observe today. That same force may have also played a role in maintaining its subsurface ocean. Jupiter's magnetic field lines trap charged particles, creating radiation belts far more intense than those of Earth. These particles bombard nearby moons like Europa, Io, and Ganymede, creating high-energy environments that challenge spacecraft and shape surface chemistry. One of the most stunning effects of this magnetosphere is Jupiter's auroras, the brightest in the solar system. These glowing ovals of ultraviolet light dance around the poles, created by interactions between the magnetic field and incoming solar wind. But unlike Earth's auroras, which come and go, Jupiter's are constant and fueled by its moons. Io, with its intense volcanic activity, constantly spews material into space. These particles are ionized and swept up by Jupiter's magnetosphere, forming a plasma torus that circles the planet. As these charged particles move along magnetic field lines, they funnel into the polar regions and trigger dazzling auroral emissions. What's remarkable is that scientists have used auroras to map what's happening deep inside Jupiter and its moons. For example, the presence of auroras at certain latitudes on Ganymede confirmed the existence of a subsurface ocean, without needing to dig or drill. Magnetic reconnection events, where magnetic field lines snap and reform, also tell us how energy is transferred throughout the system. The magnetosphere isn't just a scientific curiosity. It's a critical piece of the Jovian environment. It affects spacecraft navigation, radiation shielding, and even the potential habitability of the moons. Any future missions to Europa or Ganymede must plan around the intense radiation zones shaped by Jupiter's magnetic field. Spacecraft like Juno have flown through the magnetosphere, carrying instruments to measure particle density, magnetic field strength, and auroral patterns. These data are helping scientists model the structure and dynamics of this vast magnetic domain and better understand the internal engines driving it. Jupiter's magnetic field also gives us clues about planet formation. It suggests a deep layer of liquid metallic hydrogen, formed under pressures millions of times greater than Earth's atmosphere. As this material moves, it generates electric currents, and those currents create the magnetic field. By studying how the field changes over time, we can infer what's happening inside the planet, far beneath the visible clouds. Some of the most exciting moments in the Juno mission occurred when it plunged into the magnetotail, the region where the magnetosphere is stretched out behind Jupiter, like a comet's tail. Here, reconnection events and particle acceleration reveal how energy flows outward from the planet into space. As we look to exoplanets beyond our solar system, magnetospheres become even more important. A planet with a strong magnetic field can protect its atmosphere from being stripped away by stellar winds, a key factor in maintaining habitability. In this sense, Jupiter is more than just a giant, it's a template for what we might find around other stars. Back here in our own system, the magnetosphere links Jupiter and its moons into a single dynamic machine. It creates electrical currents, powers auroras, and shapes the very surfaces of its satellites. As we conclude this segment on Infinity Beyond, we now turn to the cutting edge of exploration. Juno's recent discoveries and how they're revolutionizing our understanding of Jupiter's interior, weather, and auroras in ways never before imagined. The concept of Earth as a rare oasis in the universe is deeply tied to a theory known as the rare Earth hypothesis. This idea proposes that complex life is exceptionally uncommon because it depends on a delicate balance of astronomical, geological, and biological conditions that may exist on Earth alone. Welcome to Infinity Beyond, where today we ask, is Jupiter part of what makes Earth so rare or so lucky? The dramatic impact of Shoemaker-Levy 9 SL9 with Jupiter in 1994 provided a real-world example of planetary protection in action. It reignited debate over how unique Earth's position is, and whether the existence of gas giants like Jupiter is essential for life-bearing planets to persist. Supporters of the rare Earth hypothesis argue that without a massive planet like Jupiter acting as a gravitational shield, Earth might have been bombarded by so many comets and asteroids that complex life would never have had time to evolve. It's not just about location in the habitable zone. It's also about stability and safety over billions of years. Jupiter, due to its enormous mass and gravitational influence, captures, redirects, or absorbs many potentially dangerous space rocks. The SL9 event demonstrated this vividly. While we can't yet prove how many threats Jupiter has deflected away from Earth, simulations suggest its presence significantly reduces the frequency of catastrophic impacts in the inner solar system. Not everyone agrees with this idea, though. Some scientists argue that Jupiter could just as easily redirect objects toward Earth as away from it. The question remains complex. The dynamics of celestial mechanics are nonlinear and chaotic, meaning small variations in a comet's orbit can lead to drastically different outcomes. So while Jupiter often acts as a protector, it could theoretically be a source of redirected threats as well. Regardless, the SL9 event advanced our understanding of impact science dramatically. Before 1994, impacts on other planets were mostly theoretical, inferred from crater counts and old models. Watching one unfold in real time revolutionized how we approached space weather, orbital dynamics, and even life insurance policies for our planet. Beyond the immediate consequences, SL9's collision offered an emotional and philosophical awakening. It reminded us that cosmic events aren't locked in the past. They're ongoing. The solar system is still an active, evolving environment, and Earth is far from immune to its dangers. This awareness has reshaped scientific priorities. Today, organizations like NASA, ESA, and even private observatories track thousands of near-Earth objects, NEOs. Space agencies are developing planetary defense strategies, including asteroid deflection tests like DART, Double Asteroid Redirection Test, aimed at altering the course of a test object via direct impact. What SL9 also teaches us is that we're not passive observers in the cosmos. We're capable of learning, preparing, and even intervening. And perhaps that is what makes Earth truly rare. Not just the right chemistry or distance from the Sun, but the presence of intelligent life capable of safeguarding itself. When we consider all the variables that make Earth habitable, liquid water, stable climate, a magnetic field, a large moon for tidal regulation, Jupiter may be another critical piece of the puzzle. Its role, while still debated, cannot be ignored. As we expand our search for life in the universe, looking toward exoplanets, distant moons, and potentially habitable systems, it may be that one of the signs we look for isn't just Earth-like planets, but Jupiter-like protectors nearby. In the next chapter here on Infinity Beyond, we move past the celestial impacts and delve deep into the very core of Jupiter. What lies beneath its swirling atmosphere? Does it have a solid center? Or is it gas and metallic hydrogen all the way down? The mysteries of Jupiter's interior are next, and they promise to be as intense and fascinating as the storms that swirl on its surface. In the vastness of space, we've discovered thousands of planets beyond our solar system. Exoplanets. Some are rocky, some icy, and many are gas giants like Jupiter. But just how common is a planet like Jupiter? Is our gas giant a galactic standard or a rare cosmic gem? Welcome back to Infinity Beyond, where today we compare Jupiter to the growing catalog of known exoplanets. Thanks to missions like Kepler, TESS, and a host of ground-based telescopes, astronomers have identified over 5,000 exoplanets. Among them, gas giants are surprisingly common, but most aren't quite like Jupiter. Many of the gas giants we've found are what scientists call hot Jupiters. These are massive planets that orbit extremely close to their stars, often completing a full orbit in just a few days. Their proximity means they're intensely heated, sometimes reaching temperatures of over 1,000 degrees. They puff up from the heat, making them easier to detect via the transit method. Jupiter, by contrast, orbits far from the Sun, in a stable, cold region of the solar system. It has a long orbital period of nearly 12 Earth years, and its temperature remains low enough to retain hydrogen and helium without ballooning in size. So while gas giants are abundant, Jupiter-like gas giants in Jupiter-like orbits are rarer. Our planet's mass, distance from the star, and relatively circular orbit make it a special case, and a template for what astronomers call solar system analogs. In fact, astronomers are actively searching for Jupiter twins, planets with similar size, composition, and orbital characteristics. These systems are thought to have a higher probability of rocky inner planets, like Earth, surviving and evolving in peace. Another unique feature of Jupiter is its moons. Jupiter has over 90 known moons, and some, like Europa, Ganymede, and Io, are worlds of their own. Very few exoplanetary systems have shown clear evidence of exomoons, though this is likely due to our current technology limits. Still, the complexity of Jupiter's satellite system makes it an exceptional example of what a planetary system within a system might look like. Jupiter's magnetic field is another standout. It's the most powerful in our solar system, shaping an immense magnetosphere. While some exoplanets are believed to have magnetic fields, we haven't yet been able to measure them directly. If they exist, they could provide protection from stellar radiation. One reason why Jupiter may have helped preserve its moons for billions of years. In terms of internal structure, Jupiter's deep layers of metallic hydrogen, vast storms, and possibly diluted core make it a useful laboratory for testing models of gas giant interiors. Juno's recent data has helped refine these models, which are now being applied to the study of gas giants in other star systems. Interestingly, many exoplanets are larger than Jupiter, so-called super-Jupiters, or fall into strange categories like warm Neptunes or mini-Neptunes. These planets blur the line between gas and ice giants and their diversity reminds us that the solar system might not be the norm. It might be an exception. Some scientists believe that a gas giant like Jupiter, forming early in a star system and staying relatively distant, might be a key ingredient for life to emerge on rocky inner worlds. Its gravity clears debris, stabilizes orbits, and perhaps even delivers water. So is Jupiter unique? Not entirely. But in the grand catalog of the galaxy, Jupiter-like planets in Jupiter-like places remain rare. That makes our solar system a precious case study, and perhaps a template for where to look next. In our final episode of this series here on Infinity Beyond, we'll zoom out one last time to reflect on why Jupiter matters and what this magnificent planet continues to teach us about the cosmos and ourselves. To truly understand what substances exist on a planet like Jupiter, we need to look beyond visible light. That's where the electromagnetic spectrum becomes our most powerful tool. Welcome back to Infinity Beyond. In this episode, we're going to explore how viewing Jupiter through different wavelengths, from infrared to ultraviolet and even radio, has transformed our understanding of the gas giant. Let's begin by recalling what Jupiter looks like in natural light. Through telescopes and spacecraft cameras, we see the iconic bands, colorful storms, and the brilliant Great Red Spot. But what lies beneath these clouds or beyond the visible eye? To uncover that, scientists employ instruments that detect other types of radiation. Infrared imaging, for instance, reveals Jupiter's internal heat. Despite being nearly 800 million kilometers from the Sun, Jupiter emits more heat than it receives. This means it has an internal energy source, likely the result of gravitational compression and leftover heat from its formation. In infrared, the planet glows, showing us hotspots where storms churn deep into the atmosphere. Jupiter's poles, viewed in infrared, reveal spectacular auroras, bright rings of energy caused by charged particles funneled by the planet's intense magnetic field. These auroras are far more powerful than Earth's and are constantly fueled by Jupiter's rapid rotation and its volcanic moon, Io, which ejects material into the planet's magnetosphere. When we observe Jupiter in ultraviolet, UV light, more secrets unfold. UV allows scientists to detect upper atmosphere phenomena like lightning discharges, high-altitude haze, and energy interactions in the ionosphere. Through UV observations, researchers have tracked how solar wind and magnetic fields alter the behavior of Jupiter's outer atmospheric layers. X-ray studies, using space observatories like Chandra, take us even further. These reveal bursts of high-energy emissions around the planet's poles linked directly to solar flares or cosmic radiation. This helps scientists study how Jupiter responds to solar storms, acting almost like a cosmic lightning rod. The electromagnetic spectrum also plays a vital role in analyzing Jupiter's composition. Spectroscopy lets us identify the gases present in the atmosphere by measuring the specific wavelengths of light they absorb or emit. From this, we know that Jupiter's atmosphere is primarily hydrogen and helium, but also contains traces of ammonia, methane, water vapor, and complex organic compounds. Moreover, radio waves give us an acoustic-like insight into the planet's dynamics. Jupiter is actually a strong source of natural radio emissions. These sounds, when translated to audio, resemble eerie whistles and crackles, signals generated by interactions between the planet's magnetic field and particles in its atmosphere or around its moons. Using these diverse observational methods, scientists have built a multi-layered profile of Jupiter. Rather than a simple gas ball, it emerges as a planet with complex chemistry, varied atmospheric behavior, and a magnetosphere that rivals a small star. Perhaps the most exciting part is that this technology doesn't only help us understand Jupiter. It acts as a training ground. The same methods are now being used to study exoplanets orbiting distant stars. By comparing spectra and emissions, we may one day identify alien worlds with similar features, or even signs of habitability. As humanity prepares to send more missions to Jupiter and its moons, these tools will be indispensable. Instruments on future spacecraft will collect data across the entire spectrum, revealing even more layers of the giant planet and possibly solving mysteries we haven't even thought to ask. Stay with Infinity Beyond as we next dive into the heart of Jupiter's magnetic field, the most powerful and expansive in the solar system. When we think of volcanic activity, Earth might come to mind: Hawaii, Iceland, or Mount Etna. But if you want to witness the most extreme volcanism in the solar system, you'll have to go much farther out, to Jupiter's moon Io. Welcome back to Infinity Beyond, where today we explore the most geologically active body in the solar system. Io is one of Jupiter's 4 largest moons, collectively known as the Galilean moons, and it stands out as the most volcanically violent. Discovered by Galileo Galilei in 1610, it wasn't until the Voyager 1 mission in 1979 that humanity saw just how dynamic Io truly is. Voyager 1 revealed what looked to be lava flows on its surface, but more dramatically, it spotted active volcanic plumes erupting from the moon, proof that Io was not only geologically active, but currently undergoing intense internal processes. This marked the first time we had ever witnessed visible active volcanism beyond Earth, excluding cryovolcanoes found later on other moons. These plumes, some of which reach over 300 kilometers into space, are driven by tidal heating. Unlike Earth's volcanism, which is caused by plate tectonics and residual planetary heat, Io's volcanism is fueled by the immense gravitational tug-of-war between Jupiter and the neighboring Galilean moons, particularly Europa and Ganymede. As Io orbits Jupiter in an elliptical path, it's continually squeezed and stretched by these competing gravitational forces. This generates intense internal friction, heating the moon from the inside out and melting its subsurface into vast magma reservoirs. The result? Surface eruptions so intense they can be observed with Earth-based telescopes. Voyager and later missions also found that Io's surface is unlike any other in the solar system. It's blanketed in sulfur compounds, giving it bright yellow, red, and white hues. These sulfurous materials don't just coat the ground. They fill the thin atmosphere as well, creating a toxic, volatile environment. In fact, Io's atmosphere is composed mainly of sulfur dioxide gas. It's incredibly thin and variable, depending on local volcanic activity. When a major eruption occurs, the atmospheric pressure temporarily increases as fresh gases are expelled. These sulfur eruptions are also electrically charged. They interact with Jupiter's powerful magnetic field, injecting ionized particles into the magnetosphere and contributing to the giant planet's auroras. In this way, Io is not just a moon. It's an active participant in Jupiter's electromagnetic system. Observations from the Galileo spacecraft and Earth-based infrared telescopes have identified over 400 active volcanoes on Io. Some are gentle lava lakes, while others are pyroclastic eruptions, powerful enough to eject material hundreds of kilometers high. The largest of these, Loki-Patra, is a lava lake that periodically resurfaces in massive overturning events. Despite its constant activity, Io has very few impact craters. That's because the surface is constantly renewed by volcanic eruptions, erasing any old features. In terms of planetary geology, this makes Io one of the youngest surfaces we've ever seen. Io's interaction with Jupiter is so extreme that it actually generates electric currents as it orbits. These currents flow along magnetic field lines and can even produce visible lightning in Jupiter's upper atmosphere, known as Io flux tubes. Scientists are now using data from multiple missions, including the Juno spacecraft, to better understand how Io's internal heat is generated, how its volcanoes evolve, and what this might tell us about similar processes on early Earth or distant exoplanets. The study of Io is not just about exotic lava, it's about understanding how tidal forces can shape and energize worlds. As we look toward potentially habitable moons like Europa, the lessons from Io remind us that moons can be just as dynamic, violent, and complex as planets. In our next chapter on Infinity Beyond, we turn our gaze outward again, from the scorching lava of Io to the icy shell and hidden ocean of its neighbor, Europa. Could this moon harbor alien life beneath its frozen surface? Water, something we associate with life, isn't just found on Earth. Around Jupiter, scientists have discovered strong indications of water in places we never expected. Welcome back to Infinity Beyond. In this segment, we take a close look at Jupiter's moons and what infrared images tell us about the presence of water and ice, hidden just beneath their surfaces. One of the highest resolution infrared images ever captured of a Jovian body shows an incredible level of detail. This image spans only about 200 kilometers, but what it reveals is profound. In this small area, concentrated water is found within an impact crater. Yet curiously, there is a ring immediately surrounding the crater where no water is detected. Then again, water appears further out in what scientists call a ray system, patterns extending like spokes from the center of the impact site. Why this pattern? It turns out the water isn't just sitting on the surface. The impactor, a comet or asteroid, struck hard enough to punch through the dry upper crust and expose the icy subsurface. When this happened, the central region filled with exposed water ice, while the immediate ring was likely superheated and momentarily vaporized. The further-reaching rays represent splashed-out material that settled back onto the surface, bringing icy fragments with it. This kind of pattern tells us a lot. It confirms that many of Jupiter's moons, particularly Europa, Ganymede, and even Callisto, have subsurface ice layers. Some may even contain subsurface oceans, sealed beneath thick, icy shells. Infrared images, capable of penetrating the upper layers of surface regolith, help us detect temperature differences and map ice distribution with surprising accuracy. Europa, in particular, is considered one of the best candidates for hosting alien life. Its surface is crisscrossed with reddish lines, thought to be fractures where water from below has welled up and frozen. Spectroscopy from both Earth-based telescopes and spacecraft indicates not just water ice, but possibly salts and organic compounds as well, ingredients necessary for life as we know it. The presence of water also plays into Jupiter's larger ecosystem. Remember, Jupiter's magnetic field is the most powerful in the solar system. These moons orbit within that magnetic bubble, known as the magnetosphere. As water vapor and particles escape from the icy surfaces, especially from volcanic moons like Io or subsurface plumes on Europa, they get caught in the magnetosphere, fueling radiation belts and auroras. These escaping particles create a dynamic interaction between Jupiter and its moons, leading to energy exchanges that light up the planet's poles with auroral rings. In fact, these auroras are far more intense and constant than Earth's northern lights, and they're fed by this very system of water, ice, and plasma exchange. Future missions like NASA's Europa Clipper and ESA's JUICE, Jupiter Icy Moons Explorer, are equipped with advanced instruments that will further probe this system. Their radars and infrared sensors will allow scientists to see beneath the surface, confirming the presence, depth, and composition of these ice layers. If a subsurface ocean is confirmed, it may open one of the greatest chapters in planetary science. Could life exist beneath that frozen shell? Maybe not surface-dwelling creatures, but microscopic life, adapted to dark, salty environments warmed by tidal heating, remains a very real possibility. The concept is similar to Earth's deep oceanic hydrothermal vents, where ecosystems thrive without sunlight. Infrared technology continues to redefine what we know about Jupiter's system. It gives us not only visual evidence of water, but also thermal clues to subsurface structure, impact dynamics, and even past geological activity. It's like having X-ray vision over a planetary scale. As we wrap up this section of our journey, it becomes clear: Jupiter isn't alone in its grandeur. Its moons hold secrets that may be even more profound. Stay with Infinity Beyond as we next turn to explore the mighty magnetosphere of Jupiter, an invisible force field larger than the Sun itself. When people think of planetary rings, Saturn almost always comes to mind, with its glorious icy arcs visible even through backyard telescopes. But did you know that Jupiter has rings too? That's right. This giant gas planet also sports a ring system, though much more subtle than Saturn's. Welcome to Infinity Beyond, where today we reveal the hidden beauty and surprising science behind Jupiter's ring system. Discovered in 1979 by the Voyager 1 spacecraft, Jupiter's rings are faint and dusty, invisible to the naked eye and even most telescopes. It wasn't until spacecraft got close that we realized the planet's massive gravity supports a thin system of particles encircling it. The rings are composed mostly of microscopic dust grains, rather than large icy chunks like those in Saturn's rings. These particles are primarily created by impact events on Jupiter's small inner moons, such as Amalthea, Thebe, and Metis. When meteoroids strike these moons, debris is ejected into space and captured by Jupiter's gravity, forming the rings. Jupiter's ring system consists of 4 main components: halo ring, a thick torus-shaped region closest to the planet, extending from the top of the atmosphere outward; main ring, the brightest and densest part, mostly composed of dust from the inner moons; Amalthea Gossamer ring, a diffuse ring fed by the moon; Amalthea Thebe Gossamer ring, even more extended and faint, linked to the moon Thebe. Despite being barely visible, these rings tell us a great deal about moon-meteoroid interactions, the behavior of dust in magnetic environments, and how minor impacts shape planetary systems. Unlike Saturn's icy rings, Jupiter's are dark and absorb most light. Observations in the infrared and ultraviolet spectrum have helped scientists map their extent and composition. Even the Hubble Space Telescope and Juno cam aboard the Juno spacecraft have captured them, silhouetted against the planet in scattered sunlight. The rings are also dynamically active. As Jupiter rotates, its powerful magnetosphere interacts with charged dust particles in the rings. These magnetic interactions can push or pull particles into new orbits, slowly altering the ring system over time. Interestingly, the lifetime of the dust in the rings is short on cosmic scales, only a few thousand years, meaning the system must be constantly replenished by impacts on nearby moons. If these impacts stopped, the rings would gradually disappear. This gives us a dynamic snapshot of a living planetary system in motion. Jupiter's rings also give scientists insight into how ring systems might form around other planets, and even exoplanets. Understanding how faint, dusty rings behave in strong gravitational and magnetic fields could help interpret future discoveries around alien worlds. Moreover, these rings help us understand the evolutionary timeline of the Jovian system. The fact that Jupiter's rings are not as massive or icy as Saturn's may be due to a different collisional history, or the absence of icy moons close enough to contribute material. As Juno continues its mission, it provides valuable new angles and data to study the rings, their interaction with Jupiter's atmosphere, and the tiny moons that sustain them. These faint arcs of dust, though often overlooked, are part of what makes Jupiter not just a planet, but a miniature solar system with its own delicate architecture. Next on Infinity Beyond, we'll zoom back out to the big picture, asking a bold question. What would happen if Jupiter disappeared from the solar system entirely? Could Earth survive without it?